first lecture, Lie algebras, and now second lecture we will introduce fields. So a vertex algebra wants to be a huge vector space, an infinite dimensional vector space on which fields act. And we want to tailor it coming from these affine Lie algebras. So first of all, it wants to act, so we need to define representations. Well, for an affine Lie algebra, these are quite easily defined. So what do we do? First of all, let me define just the positive part of the affine Lie algebra to be the obvious thing. I just omit negative powers in T. And now what can we do in order to define a module of the affine Lie algebra? We start with rho to be a module for G. So I will call G often the horizontal subalgebra. Then what we will often do is we let K act on rho by multiplication with K, with a scalar K. And this scalar we will give a name. So this is what you were probably referring to when asked. And this scalar I will always call the level. And the action of D is not important for reasons that I will explain later. So I will just say that it acts as 0 on the representation. Now, if I have a module for my Lie algebra, I can immediately make it to a module for the positive part by just saying that well, by saying what, I just say the rest acts as 0. So all non-constant terms in T just annihilate this module. And once one has this, one can define a module of the affine Lie algebra. We would then call this the Verma module coming from rho at level K. So K here, this is an arbitrary complex number. And then we define the module denoted by the symbol Vk, not G, rho, to be the induction of this module to the affine Lie algebra. So what does this mean? It means it has as a top-level subspace this module of our finite dimensional Lie algebra. All the positive modes, all xn, where n is a positive integer, act as 0. And all xn, where n is a negative integer, act freely. So, okay.
Can you write down explicitly which vector spaces this is?
Yeah, I just wanted to do this. So in particular, it's the so as a vector space, it's just the polynomial ring. So let x1 up to xd be a basis of our Lie algebra. Then as a vector space, this module is just the module of the finite dimensional Lie algebra times polynomials in all these infinitely many negative modes, the x in the -1 modes, the -2 modes, the -3 modes, all others. Right, so it's so in particular for the beginning of this class, only one module will be important, namely. Yeah, I should write down here tensor. That is it. And now if we take a row to be the trivial representation, and let me write the trivial so what I mean is that G just acts on row as 0. Then this induced module is called, gets this symbol, V with an upper index K of G is yeah. And this vector space we will eventually give the structure of a vertex algebra. Not for the moment yet, it will this afternoon, I hope. Yes?
Someone is annoyed that you've used D both for the dimension of the Lie algebra and for the element of the Lie.
Annoyed is a very strong word. No, I was just confused for a second, but I'm
Yeah.
on board now. There's two different things.
Yeah.
Clearly different. It's fine.
Yeah, this is indeed. Yeah, and here's the ID. Yeah, this is not ideal, definitely. The derivation will almost not appear anymore. So the confusion will disappear.
Sorry, what was I lost the horizontal subalgebra term?
Yeah, so I can identify the Lie algebra G with the constant polynomials here, and so I will call it. It's just a name for it, horizontal subalgebra. Yeah, the embedding of G in G hat. You have infinitely many embeddings. This is the canonical one, and so we will call it the horizontal one. It lies horizontally in the middle. So, okay, and in particular, this module has a nice Poincaré-Birkhoff-Witt basis given by vectors, and now we just have to take ordered polynomials, ordered monomials here. So this means it has a basis. This vector, by the way, I will always call vacuum vector. The names will reappear. And so what can I, and then it has clearly a basis of given by monomials, and I just have to say how do I order it. I take the leftmost index to be the smallest one. And if two successive indices coincide, then I just have to say how the upper indices are related. But of course, I started with a finite dimensional Lie algebra, so I have an ordered basis here, and so I use the ordering here. Okay. And this is yeah. Hmm?
These things all anyway commute, right? These people, they all commute in any case?
Who commutes?
These X's.
No, they don't commute.
Oh, what?
No, they don't commute. They very much don't commute, right?
I see.
Right? So they don't commute. So the ordering, if I reorder, But what happens if I reorder? Then I get an additional summand where the index becomes where the monomial degree decreases by 1. So this allows you to deduce that this gives you indeed a basis, right? Because
But does it matter this order you chose? You
No, it doesn't matter at all. It's just for illustration, right? It's definitely worth to spend time on this, right? A vertex algebra will be an infinite dimensional vector space. For example, this one that will have a very nice basis, at least in the simplest cases, and we will start with the simplest cases. So here, right, as a vector space is nothing but the polynomial ring in infinitely many variables. But these variables don't commute, right? So that means it's, yeah. And so the ordering makes sense. Okay, so a vertex algebra wants to formalize the symmetry algebra of a two-dimensional conformal field theory. This means it wants to be something like a quantum field theory. That means it wants to have operator-valued functions on certain vector spaces. So we have a vector space. More general, we have a zoo of vector spaces parameterized by representations of our finite dimensional Lie algebra.
This last line there,
Hmm?
if ni is equal to ni plus 1, then ai, can you comment on that?
Yeah, I chose here an ordered basis of the Lie algebra, and the upper index is the ordering of the basis of the finite dimensional Lie algebra. So let's.
Do I need this for when ni is ni plus 1, and why don't I need it in general?
Yeah, if they are not what does this mean? Is we first to the right we have those modes that have the highest index, the -1 ones, right? So for example, why don't I do an example? Yeah. We have SL2, which has a standard basis. It's three-dimensional, and maybe let me write down. SL2 are traceless 2 by 2 matrices, and this would be a standard basis, and I fix any ordering on those, right? And so then and then what would be a typical vector of the infinite of the affine of this vacuum module, this VKG? I could, for example, here start with an x1 minus 1. Then I could have an x3 minus 2, for example, and an x2 minus 3. So I will always let this index to be more and more negative to the left. But it could be that here I have another index with a minus 3, and then I have the convention here that if here two indices are the same, then the rightmost index is smaller than the left one. Did I write this correctly? I just have to fix an ordering. It doesn't really have any importance.
But I mean, the point is that somehow that this is supposed to be a basis.
Yeah.
So I can sort of see why you can arrange them in decreasing order.
Mm-hmm. In order to get a basis, I just have to fix an ordering. I just have to fix one. I could fix. I could equally well have put a greater equal here. I could have chosen any ordering on my finite dimensional Lie algebra. It's just to get a basis, right? Because if I reorder, then reordering gives me just monomials or polynomials of lower degree that I can. So this means it's not a linearly independent vector.
Actually, I'm a little bit confused. It looks like reordering gives you polynomials of higher degree.
Polynomial degree, right? It's, if you reorder, for example, if I take this one, right? This is, I would say this is of polynomial degree 4, right? And if I reorder, then I have to take the commutator of these two. But what will this commutator give me? It will give me an x3 with mode index -6. So it will give me a polynomial of degree 3.
Actually, I wrote a question.
Yeah. Hmm?
I would have thought like usually with like quantum mechanics or something, so changing the order of things, the difference should be small in some sense.
Yes. Hmm?
But here, the thing which is created by changing the order
Mhm.
in the Verma rather than spell.
Yeah.
Can you explain how to think about this fact?
That I can, yes.
Do it now. It was just confusing.
Yes. I, let's see whether I can give you a good explanation. So often, if you quantize, you think about of having a filtration, and then if you and then your associated graded becomes your classical object, or maybe the leading one. And here you would think about as the mode index somehow becomes your filtration degree. The more negative, the higher in filtration. This means that means the more subleading in quantum corrections. So for example, if you think about this one here, you identify your Lie algebra itself with the -1 modes. So this would be your leading piece in filtration, your quantum mechanical problem, and then you have more and more subleading pieces which are of higher mode index, and that can be formalized, but that would be a long story. But yeah, you should think about it counterintuitively in the sense that the higher, the more negative the modes, the more subleading they are. They are quantum corrections. Okay. Good. Yeah, I'm glad that you are asking so many questions. It means I'm much slower than I expected. So, but that's good. I mean, we have a lot of time. Okay, now I define this one, and I call this a field. So this means to an element x in my Lie algebra, I define a capital X, and I call this a field. And now let's study what kind of properties this is. Also, let me write just V for this this thing here, for this module of the affine Lie algebra. So this means this one here, what is it? It is a formal power series in Z and Z inverse, right? N runs over all integers, and the coefficients naturally act on it. So I will here I will not distinguish between the element of the Lie algebra and its operator that acts on the module. I will never do that because otherwise the notation becomes way too much. Okay, now we do a computation, namely we compute the commutator of two such fields.
I don't understand. How do you multiply such things?
Yeah, this is what we will now explore.
Sorry, so the definition of a field is just an element of G? Is that what you're
No, a field, yeah. We take an element in G, and then we have the associated field, capital of X, and this one. And now we have the problem is how do we...
I don't understand in what way X is related to all these XNs.
So we take an element X in G, then we have the corresponding Xn, which is this X times t to the n, and then we have the capital X, which is what I wrote down. Right, so you fix the element in G, that gives you an infinite set of these modes and the corresponding field.
And it's just the formal series.
It's just a formal series, and now we need to understand how can we take products of those. Exactly what you're asking, because of course if I take just a field times another field in the same variable, that doesn't really make much sense.
So X of Z or X of minus Z?
x of z, yeah. Okay, so now we take another element in G, let's call it y, and the corresponding field y. And now, first of all, what do I do here is I change the name of my formal variable. So I take here two different ones. And so this means the product is now a formal power series in two variables. That already makes much more sense, right? Okay, let's and in fact, we are at the moment not interested in taking the product, but the commutator of two such fields. So let's do this. So what do we mean by this? We mean the product of the one and then and now we write this down. But this is exactly the commutator of these modes acting on our module. And now we can insert the formula that I wrote down for the commutation relation of two elements of the affine Lie algebra. What was it? We get here the element of the Lie algebra corresponding to the commutator of x and y, and the mode index becomes additive. And then we have here and now I would like to have here the same exponent. I would like to have here a w to the minus n plus m minus 1. So I added an So in order for this to work out, I have to multiply here w to n. And then there was a second contribution in the commutator, which only appears if n plus m is equal to 0, in which case it comes with this central element k, but the central element acts by the scalar k. Can everybody see? I think I will continue here. So up to now, I just plugged in the formula for the commutator. And now let's look at this sum first. First, I can define a new index, and I replace m by n plus m. So then this becomes, let me call this L. So here I set L is equal to n plus m. So that's good. And then I'm still left with the sum here. over n. Okay. And then for the second sum, I can replace m by minus n. Okay, and then I still have this level times the pairing of x and y. Okay, and now let's look at this. How do these two expressions compare? We see this expression is exactly the derivative with respect to w of this expression, right? Yes?
You replaced k by h, so I feel like you've...
No, this is a k, this is a k. This is my k.
Oh, it's k now.
Yeah,
It's the-
yeah. Yeah, I replaced the capital K by the lowercase k because the capital K, the central element, acts by the scalar k. It's now always acting on V. It's not the computation in the affine Lie algebra, but as operators on this module in which capital K acts by lowercase k.
Right, so I guess my question is, when you're defining a field, you're picking a module.
Yes.
Okay.
Yeah. Okay, and now let's look at this expression. What is this expression here? Well, how did we define a field? It's the sum over, let me call n now L, the sum over L and Z, XL, Z to the minus L minus 1. So you see, this is exactly the field corresponding to the element x, y, the commutator, in the formal variable w. So this becomes the field corresponding to the commutator. Let me... and then times this expression here. And let me give this expression a symbol. Let me call it this delta z minus w plus the derivative of this delta times the scalar k times the pairing of x and y. Okay, so this thing here is called the formal delta distribution. And the name is justified by the following property. So let's do a quick computation that justifies this property. So at the moment, what did we do is we defined this field and we did this computation where we essentially plugged in the commutator of that we get from the affine Lie algebra and then just rearranged our summation so that this delta distribution and its derivative appeared. Well, if it is really a delta distribution, then maybe from a physics point of view, that's not bad because you would think about it as these two fields. They do commute, except if they are very close to each other. Okay, so let's take a power series in the variable w. So then what happens if, and let's take the product of A of this power series with the delta distribution. So then and and now we want to rewrite it such that we get the same expression except that we replace W by Z. So so this means we make this expression now symmetric. This means we set L equal to M plus N plus 1, so that we set, let me write this, minus L minus 1 to be equal to M plus N. So then the sum becomes the sum over N and L, W to the minus L minus 1, Z to the minus N minus 1, and M becomes now minus N minus L minus 1. And now we see this expression is completely symmetric in N and L, so I can now go back here, but just interchanging the role of these two, and then go back here. So I don't have to do that explicitly, but just by going back that way, I get the same product, but the formal variable replaced. But this is exactly what you, and now you can, of course, that's exactly what you want the formal delta distribution to satisfy, right? By if you multiply by something in one variable, it's the same as by multiplying it by the same expression in the other variable. So in this sense, it satisfies the property of a delta distribution, but now on formal power series. So hence formal. Yeah, we don't integrate here because we are only working with formal power series. The name is simply just justified by this property that formal delta distribution multiplied by a formal power series in the second variable is the same as delta distribution multiplied by the same formal power series but in the other variable. No integration, it's just the property that you want.
Is like the derivative of the delta distribution with respect to omega the same? Like, does this also hold if I like replace omega by z there?
No, but as something. So in particular, what do we see here? If we take now the formal power series z, right, then we get z times delta is equal to w times delta is equal to z times delta. In particular, z minus w times delta is equal to 0. Right? So this means in particular what we see here from this one is we see multiplication by z minus w with a formal delta distribution gives just 0. And now to your question, this can be somehow generalized if you want to include derivatives of the formal delta distribution. The following lemma, which I don't prove, it's not that difficult. If so you take a formal power series in these two variables, And then,
So, Thomas, are you sure about the sign? I mean, you didn't do this last step, but I mean, you start with A of W delta of Z minus W.
yes.
And then you say it's totally symmetric. So I would expect to get A of Z delta of W minus Z at the other end. Am I being stupid?
You're right. Now, if you, we can of course replace here n by negative n, and then also shift by 1, and then you're asking what's the difference between delta z minus w
No,
and...
I'm asking whether at the other end it should be delta of W minus Z.
Yeah. So here, if we take the delta distribution here and we replace n by negative n, then that would swap these two. And then now if I do an additional shift by 1, to so by resumming, you see that delta of z minus w is the same as delta of w minus z. Okay. Yeah, so, but that's maybe a good exercise. It's a very quick one. But yeah, good question. Okay, so the lemma says if I have a formal power series that has the property that z minus w to the n annihilates multiplication by this is equal to 0, right? Here we saw an example that has this property for n equals 1 for some positive integer. Then this formal power series is in fact a sum of the formal delta distribution and its derivative. So here's the ith derivative of the formal delta distribution, and here the coefficients are some formal power series in one of the variables. Okay. So, and this is in some sense the answer to your question. It's yeah, and yeah. So one direction of this lemma is quite easy, right? Because now you can to see that, for example, the derivative of delta is annihilated by z minus w squared. You just multiply by z minus w and take the derivative, and you see that the other direction is then harder of this lemma. Okay. Yes?
I got z minus w to the power n times n equals 0. Is that in the formal power series?
It's in the formal power series, yeah.
Okay. I'm not yet seeing why this sort of would happen. Are we evaluating this?
If you believe that A omega tells the Z minus W, just replace A omega by then A, that's the same as A was
Right.
which is Z minus Z is 0.
Yes.
Yeah.
Check. Thank you.
Okay, let me maybe conclude this lecture with a definition of a field. So, V a vector space and everything is super, as a reminder. A field is just a formal power series where the coefficients act on our vector space. exactly as in the example for the affine Lie algebra. And we say A is homogeneous. So here, Vi, this refers to the Z2 grading on the vector superspace, and it is homogeneous if an times Vi, well, if, for example, if both of them are odd, then the product is, then an on an odd element is an even one, and so on. Okay, yeah. So the next thing, what I'll do then in 2 hours, I will introduce another product, which is called the normal ordered product. Why will I do this? It will allow us to replace the formal delta distribution by something nicer. So then the products will look much more pleasant, and then I will finally define a vertex algebra. Any more questions? Yes?
I was trying to understand why you wrote down these specific things you were writing here. And the best I could figure out is that they satisfy some equation like z ddz plus the derivation plus 1 equals 0.
What are you referring to now here?
Why do you write this thing with the form x of z? And one reason I could imagine is that x of z is exactly the kind of thing which satisfies the equation I just said. Derivation plus z ddz plus 1 kills it.
Can you say it again? You mean this now, yeah?
This thing, yeah.
Mm-hmm.
So you could take derivation plus z ddz plus 1. So I was curious, what's the significance of that?
Right.
Any significance of that fact?
Yeah. Right. Very good. It satisfies this property. That's correct. And it comes. You're just already going a lot ahead of this course. So this will belong to a vertex algebra, and we will learn that a vertex algebra in particular has another infinite dimensional Lie algebra, a subalgebra called a Virasoro algebra. So it will, and it will be correspond to a field that again has such a formal power series. One takes here the convention to take a 2 here. That's not important. This L0 will be identified with a derivation, in fact with a negative, with minus the derivation. And what you just said is exactly the statement that about the product of the Virasoro field, this one with x. So the equation that you just told everybody is exactly the one that this x is. Let me write down. It will turn out that so this is then outlook to coming lectures. We somehow don't like this formal delta distribution. And so we will introduce in the beginning of the next lecture a new product, which we will call the normal ordered product. Which will have the nice property that the actual product of 2 fields is nothing but the normal ordered product plus polynomials in the difference of the inverse of the difference of the formal variables, where the coefficients are fields again. So somehow very nice, and the observation you figured out is nothing but a special norm, a special such product, which then, of course, a very significant one. Yes?
So I'm now confused about this definition a little bit. So you started with a vector space,
Yes.
but the vector space comes with a grading, the V. The V also already has some grading.
Yes. It is Z2 graded.
Okay, yes.
Right, and this here is taken modulo. I mean, well, this is
Okay.
right. This is in Z2, right?
And yeah, and A is homogeneous. It doesn't have to be. It's like it says if not such that.
Yeah, and the point, every field is will always be a linear combination of an even and an odd field, and it's most convenient to introduce things always for homogeneous ones and then extend by linearity. If super confuses, I just introduce it because it would be a waste not to introduce it. It's just everything works equally well for super. If it's confusing, you can always just ignore it and think about everything to be in the Lie algebra setting, in the even setting. So.
Can you say once more what question this thing answers?
Yeah, Vivek observed that this field satisfies, you can, so we have we had this derivation, which at the end of last lecture I added a tilde to it, so that you don't confuse it with a dimension. That's the derivation of the Lie algebra. Its commutator, what is this? This just is, it just gives the commutator of the derivation with xn is n times xn. Okay. On the other hand, I can take the literal derivative of the field, of this field, and what would I get here? I would get a minus n minus 1 and now, and in particular, I can take the derivative z times d dz, so that I just get the same power here. And now you can compare them, and you see, the sum of these two just gives us the field x again, right? So we see the field x satisfies the equation d tilde, the commutator with d tilde with the derivation, plus the z times the derivative, just gives us the field x back again. And the question was, what is the significance of it? And that was a question that came way too early in this course. But the answer is motivated, what I will start by in this afternoon. Namely, we will introduce this normal ordered product. And there will, in fact, turn out to be a very special field called the Virasoro field. And this Virasoro field has in particular the property that this d tilde will be identified with this negative L naught. In fact, negative L naught plus a suitable scalar, which of course is irrelevant for the commutator. So that, and then this equation is a consequence. I mean, it's encoded in this one. Right.